Okay, I'm back. Sometimes it takes me a minute to step back and look at what I've done to catch the mistake. The first mistake was when I moved the k's and everything over. These are actually all positive. That's actually why I did that, right? To make them all positive on the other side and to show that we're adding these three vectors. Here's the other mistake, and kudos on you if you got it. If this derivative takes that solution we had, a cosine omega t plus phi, and if taking a derivative pulls out an omega, well, taking two derivatives, of course, pulls out two omegas, right? Did you get that? So I'm going to fix this. This is m omega squared, okay? Big enough. All right, so, but now, piece of cake, because we're just adding these vectors here, right? So this vector, my answer, right? The answer is just the length of this vector at this angle. So if I add the two that are collinear, well, adding two vectors that are collinear in the opposite direction is pretty easy, right? That's just k a minus m omega squared a, right? And then that's this side. I square it, and then I just use the Pythagorean theorem, right? The Pythagorean theorem says that, well, it's that side squared, right, plus the other side squared, the omega a squared, and that just equals my answer here, is f naught squared. So you might be saying to yourself, yeah, but they're rotating. Yeah, they are, but their relative orientation isn't changing. Check that out, right? So in fact, you're just solving like Pythagorean theorem, one of the easier questions probably you've done in a while. So we can simplify this to get some sense of it. We can simplify it. I'm going to erase some of this here and say that our solution is that x is a cosine omega t plus phi as long as this statement is true. So let's pull out a, because that's what we're curious about, right? We kind of want to know what bang for your buck. If you apply a little oscillating force, you can get a big amplitude, and I'm going to show you why here. So we're going to pull a out as a common factor. So this is a squared k minus m omega squared squared. I just pulled out the common factor of a squared, right? Plus b omega a squared. And in fact, I can pull out that factor of a as well and just do this. And this is f naught squared. Yeah, okay, so now what? Oh, here we go. So now a is equal to f naught squared, not squared, we're going to take the square root of both sides, divided by the square root of, well, this thing. Now I'm going to do something you might not see to do, but I'm going to do this by saying that I'm going to pull out m as a common factor here, and I get k over m. In fact, I need to pull out an m squared, because it's a k over m minus an omega squared plus b omega squared. Wait a minute, k over m. You've seen that before. K over m now, this is just the natural frequency of the thing squared. Omega is the actual driving frequency, but omega naught's just the natural frequency. So we can rewrite this as a is equal to f naught divided by the square root of m squared omega squared minus omega naught, omega naught squared, minus omega squared plus b omega squared, right? So check this out. What this is saying is that if omega and omega naught are really far apart, if you try and drive this thing at the frequency that's not its natural frequency, this number is going to be pretty big down here. The amplitude you get, small. But as this number gets close, as omega gets closer and closer and closer to omega naught, this whole term can be 0. That's in fact the biggest amplitude that you're going to get. The biggest amplitude that you're going to get is f naught all over just this b omega term, right? So the B does limit the amplitude you can get, and you can imagine that if we didn't have any damping at all, well, we can't really do the problem analytically, because pretty soon, right, what happens? It blows up. You get infinite amounts of amplitude, which isn't realistic. So we've found now what bang you get for your buck. And if you are interested in circuits, or you're looking to be an electrical engineer, this might start to be looking kind of familiar to you. In fact, these three vectors then become the resistor, the capacitor, and the inductor, and what's here tells you, how much current you get for your voltage. In other words, this is the impedance. But that's a story for another day. Catch you next time.